The screen is clear?
Yes.
All right. Assalamu alaikum wa rahmatullahi wa barakatuh. I'm Jude Abu Hijja, and I'm honored to represent the LAMBDA Physics Group at the University of Jordan. Since its establishment in 2015 by Professor Hanan Saadeh, LAMBDA has grown into a vibrant community of physics enthusiasts. Our mission is to make the beauty of physics accessible to everyone, whether you're a student of science or simply someone with a curious mind. After all, physics is not just a subject, it's a way of seeing and understanding the world. As we continue our journey, I am excited to share that next year we'll also be celebrating 10 years of LAMBDA, a decade of curiosity and inspiring love for physics. It's an incredible milestone, and we look forward to celebrating it with all of you. If you're interested in joining us, please scan the QR code to learn more. Today's event, Light Up with Physics, أشرق بالفيزياء, combines the spirit of the International Day of Light with the upcoming 2025 International Year of Quantum Science and Technology. By celebrating the essential role of light and exploring the wonders of quantum science, we aim to highlight how these fields come together to shape our understanding of the universe. Your feedback on today's event also matters to us, so don't forget to share your thoughts using the feedback form linked to the QR code provided. Now, it's my pleasure to hand the floor to Professor Hanan Saadeh, who will introduce our esteemed guest speaker.
Thank you, Jude. Let me share my screen. I hope everybody can see the screen now. Jude,
Yes, your screen.
the audience.
Yeah, it's visible.
Okay. So let's make it full screen. Bismillah ar-Rahman ar-Rahim. Assalamu alaikum. Welcome, Dr. Sabieh Anwar from Lahore University of Management Sciences, and also all our friends and colleagues in the University of Jordan and in other universities in the region are most welcome. We are very grateful to have you all on board. Thanks to the University of Jordan for enabling us to have such a virtual event on the Microsoft Teams. Before I introduce the esteemed speaker, I would like to share with you the word cloud of the participants of this event. You can see that the majority is balanced between Pakistan and Jordan, which is good, but also we have other colleagues from Egypt, Morocco, Turkey, United Kingdom, and also some in the United States and Saudi Arabia. So it's a pleasure to have more than I remember the number of registered people was more than 150. I hope that most of them can join. Up to now, the number is not the total registered attendees. So back to the esteemed speaker, Professor Sabieh Anwar. Professor Sabieh Anwar is recognized in terms of research, education, and also leadership. But among a lot of pioneering research work that he did, he is well recognized and as one of the most influential participants, physicists in Pakistan by building the so-called Phys Lab at LUMS University, which was replicated in many Pakistani universities and probably also in other universities in the region. He is also well known for teaching and research in quantum mechanics, and most recently, in a couple of years ago, he co-authored a book on quantum mechanics in the single photon laboratory together with some of his ex-students. And also, most recently, he was publishing a series of quantum mechanics course called 30 Hours Marathon on Quantum Mechanics, which is freely available online, and I'm used to recommend it to my students. For us in the University of Jordan, Dr. Sabieh Anwar is not a guest because we had the honor to host him in person 7 years ago. Now I feel it's a long time. 7 years ago, he was with us in person at the School of Science in the University of Jordan. But since then, and also before that visit, we were collaborating with Dr. Sabieh. This is not the first online meeting with Dr. Sabieh. And I personally had the honor to visit his lab in 2016, and I wish I will repeat such an opportunity again with my students. Beside this picture, I would like to end by saying that Professor Sabieh Anwar, beside his very impressive CV, he's one of the most, in my opinion, one of the most influential voices of physics, and particularly of experimental physics, not only in our region, but also in the world. And I will end with this picture for Dr. Sabieh, because I think if I allow him to introduce himself, he will leave the word leader, researcher, whatever, and he would like to call himself probably a teacher or an educator. So I will stop by this because I don't want to waste your time. There is a captivating talk awaiting you, a very motivational and useful talks for all of us, students and colleagues. I personally, whenever I have a chat or a meeting with Dr. Sabieh, I feel impressed with a new perspective and new ideas. So I leave the mic to Professor Sabieh. Dr. Sabieh, you are a presenter now. I hope you can share your screen.
Yes, all right. I will share my screen in a minute. So, Bismillahirrahmanirrahim. I hope you can all hear me. So, first of all, I would like to thank Professor Hanan Saadeh. She's always been very generous, always been very kind. We've known each other for a number of years now, almost, I think, 8 or 9 years. She hosted me in Amman as well, and I really follow her achievements, and above all, I follow the achievements of the LAMBDA Physics Group and how the group is cultivating an interest in physics among students in Amman and beyond. So thank you very much, Dr. Hanan, for inviting me. So I would like to share my screen now.
Yes, please.
All right. So I hope you can all see my screen at the moment.
Yes.
All right. So first of all, what's on everyone's mind is the plight of innocent human beings, innocent civilians, innocent Arabs, innocent Muslims, and the apathy of our rulers. We pray to Allah that the plight of our friends and brothers and sisters is changed, and we can all live in freedom, all live in human dignity, and may Allah raise the ranks of the martyrs. So it's very hard to talk about science, especially in the Arab world, in Jordan, and not talk about what's happening just around the corner. In our classrooms here in Pakistan, we kind of always keep this at the back of our mind. I know there are many Palestinians here in this room. Jordanians are also Palestinians. So with some level of anger, some level of hatred, and some level of admiration of the bravery and courage of our people, let's begin today's talk. So I would really like to talk about practical quantum physics. So when we learn about quantum mechanics and quantum physics in our curriculums, it's kind of relegated to the textbook. We do lots and lots of calculations. Some of them are very strange calculations, especially when we enter the realm of quantum information. But we never see quantum mechanics. We never see quantum physics in action. The best we could do is probably use lasers in a laboratory. I know lasers are very close to your heart as well. Uh, Lasers are a byproduct of a quantum mechanical description of atoms and atom matter interaction, atom light interaction. But really, the quantumness of light is generally hidden from our view. The photoelectric effect is an incomplete description of the quantum world. Uh, so we really need to kind of see quantum mechanics in its pristine beauty. So now what we've done here in Pakistan, and probably for the first time in the region, is kind of inspired from other initiatives around the world. We've kind of developed a suite of experiments, a suite of different kinds of ideas, practical ideas that can make quantum mechanics come to life. Quantum mechanics comes out of the textbook and it stands in front of you and it kind of invites everyone to have a look and play with it. This is the idea of our quantum laboratory. So this work in our quantum laboratory is really done by students. So not something sophisticated which requires state-of-the-art equipment, sophisticated equipment. It's all done really by students. And these are undergraduate students mostly. For example, if you look at the top right, Abdullah, he is now a PhD student in optics at the University of Rochester. And this is the initial team from another university in Pakistan, the engineering university, who came and worked in my laboratory and helped in developing all of these experiments. Hamza, this person who's standing at the back, he's a PhD scholar at the University of Oxford. Faizan is kind of starting his PhD at the University of Massachusetts. Bilal was working in a software house until recently, and now he's back to academic research. And all of this is a part of a corner that we have developed in our laboratory called the Goshai Ibn Sahal. Ibn Sahal, as you know, is a famous Iraqi Arab physicist to whose credit lies the law of refraction. So all of this work is actually done by students. There is really no rocket science in any of this. It's just a clever and an intelligent use of resources. You put them together and quantum mechanics comes to life. And how does quantum mechanics come to life? That's what I'm going to explain in a minute. Now, this is one photograph of our single photon quantum laboratory. Bilal is working with 3 master students, and they are kind of looking at different facets of the quantum properties of light. And this is a truly quantum manifestation of light, as I will explain in a minute. Here is another view of the quantum laboratory. This is what it looks like in practice. In our physics laboratory, which we call the Phys Lab, which is in a university in Lahore, Pakistan, the university is called LUMS. We also have other kinds of laboratories. And if you notice, all of these are laboratories that have been built from scratch. A lot of homemade equipment is being used. A lot of instruments are being developed. Some of this instrument is also being commercialized so that we can help other institutions in Pakistan and beyond. And we get lots and lots of students from all around Pakistan, not only university students, but lots of school students and college students who come to work with us on different ideas. So we share, in a sense, the vision of the LAMBDA Physics Group set up by Professor Hannan Saadeh at the University of Jordan. So we are kind of brothers and sisters in crime, in a sense. All right, so when we talk about quantum mechanics, generally a few ideas come to our mind. It's ideas that revolve around the quantization of energy, superposition, entanglement is one of the hallmarks of quantum mechanics. Quantum mechanics is incomplete without interference. So these particles behave like waves and they interfere constructively or destructively, and you get all kinds of eerie phenomenon stemming from interference, superposition, and entanglement. Of course, we can never lose sight of the quantum uncertainty principle as proposed by uncertainty. And one of the paradoxical paradigms in quantum mechanics, of course, remains measurement. So you can do different kinds of experiments in your undergraduate or graduate education in a university to explore quantum mechanics. For example, one experiment that our students do is looking at the spectrum of the bright sky and the spectrum from the sun using a simple spectrometer. So they just point this device is a small telescope towards the sky or towards the sun, and they connect the received optical intensity to a spectrometer, and then they look at the absorption spectrum. Of course, these absorption bands that you see are a signature of absorption by molecules, and that absorption would depend upon the inner energy level structure of those molecules and atoms, which comes from quantum mechanics. So all of these are quantum mechanical phenomena, no doubt. But when I say the quantumness of light, it's something beyond that. When I talk about light, one way of looking at light is that it's just a wave, and all the properties that a wave has, light also possesses those properties. But quantum light really means that you're getting down to the level of photons. You are looking at a photon eye to eye, and probably you just have a single photon in your apparatus. So when we really talk about single photons, we are generating new kinds of states that are called Fock states. So a single photon state is a Fock state with a number eigenvalue 1. So there's just one photon in the system. And this is where the quantum properties of light comes to the fore. So how do we generate these single photons? So here is an overview of the single photon laboratory. All of it is actually summed up in this diagram. So what happens is that a laser comes in. It's a 405 nanometer laser, and it falls on two nonlinear crystals. Those nonlinear crystals are oriented in a special direction, and most of the light passes straight through the pair of crystals. Nothing happens. But a very small fraction of the photons, they undergo a nonlinear down conversion process. And through this spontaneous parametric down conversion process, two photons are created that have double the wavelength, half the energy. And these photons have their quantum states, which are entangled with one another. Now, remember that these are single photons that we're talking about, one photon at a time. And what do we mean by entanglement? Now, entanglement is a correlation between these two pairs of photons. They come at roughly the same precise moment of time. So they're entangled in time. Their momentums are also entangled. So one has a momentum, say, going to the right and up, and the other is going to the right and down by the same amount. So their momentums, their linear momentums are entangled, and so are their polarizations. So if one of the photons is, say, horizontally polarized, the other might always be vertically polarized. If this photon is vertically polarized, the other is horizontally polarized. So you can have complete quantum correlation, which cannot be described classically in the time, in the momentum, and the polarization of photons. So now two photons emerge from the system, and they pass through different kinds of experiments on each of the arms. One arm is called the idler arm, the other arm is called the signal arm. And then you have these detectors, A prime, B prime, that have the capability of measuring and responding to single photons. So when one photon hits a detector, it produces an electronic pulse, a small electronic pulse of a width of roughly 9 or 10 or 11 nanoseconds. And then this These pulses are shaped, they are counted, and all of this data is then transmitted to a computer for analysis. And then you can look at graphs of, you can look at the statistics of the occurrence of photons on the different detectors, A prime, B prime, and infer from the statistics the quantum mechanical wave function of these photons. And these photons can interfere. You can do all kinds of strange experiments that have now become the hallmark of quantum mechanics and quantum information. So this is a simple overview, nutshell view, panoramic view of the single photon laboratory. Now, this is what it looks like in a schematic form. It's very simple. Everything is placed on an optical table or an optical breadboard board. Laser comes in. This half-wave plate changes the polarization. This is our pair of crystals. Most of the photons, the pump photons, just go unimpeded. Nothing happens to them, but you get these two Sigler and Edler photons that are entangled with one another, and everything falls onto detectors. And then you can, on each arm, you can do different kinds of experiments. This is a photograph of a setup. The lab is not normally as clean as is shown in the diagram, but we've taken this photograph just for the purposes of presentation. So this is how it all looks like in reality. So laser comes in, these are the pair of crystals. This yellow pipe is a pipe that brings in dry nitrogen because the crystals absorb moisture and you want to keep those crystals dry. And then these two beams emerge, they're entangled photons, and then you can do any kind of measurement, system manipulation, any kind of unitary operator, as it is called in quantum mechanics, on the two arms. And then everything is coupled into an optical fiber. These orange lines are optical fibers, and these optical fibers go into the pulse counting modules. And these modules are kept in dark because since they're very sensitive, you don't want to expose them to ambient light. And these are truly single photon detectors. You buy them. We can't make them at the moment, so you have to buy them. And they just respond to a single photon. The human eye, by the way, the human eye is extremely sensitive. Its retina triggers or activates upon the imposition of, say, 40 to 50 photons. There are some marine animals, especially those that live in the darkest trenches of the oceans, whose eyes respond to 1 or 2 photons. So these single photon detectors are the kind of ultimate limit of light detection. Now, when a single photon impinges upon a detector, we get this kind of graph. This is the electronic signal that comes out from a single photon incidence event. And then we shape it so that we get rid of all the ringing effect, and we get a nice Gaussian style single pulse. And we use different kinds of detectors. We can control the pulse width. Each detector has a dead time. And even in the dark, these detectors give some short noise as well. We all know what short noise is. So there are some dark counts. So our real count from the real experiment have to go way beyond the dark counts. And then we can program everything on an FPGA. Now, and an FPGA is a board called a field programmable gate array, which has the capability of counting these photon pulses. And not only can it count A's, B's, B prime, A prime, which are single photon detections on the 4 photons, we can also look at coincidences between AB, AB prime, A prime B, A prime B prime. We can look at 3-fold coincidences as well, A, B, B prime. So remember that if photons are produced in pairs, whenever there is a detection on A or A prime, there has to be a coincident detection on B and B prime. So whenever there are coincidence detection events, we know that single photons exist. We know that those triggers are really from single photons that are coming out from the down conversion process. So this is how we artificially create single photons. I'll explain this in a bit more in a different perspective in just a minute. So what we really have is a laser that is shining light on this pair of crystals, and 2 photons emerge, A and B. Suppose I have these two detectors A and B. So if my B clicks and I just look at detector B, I cannot be sure whether this click is coming from a single photon or not. It could just be random noise. But whenever A clicks and B clicks, and both of them click at the same time, this is called a coincidence. So if B clicks and there is a coincident click on A, I can be sure that the click of B is accompanied by another photon being detected on A. So if I just look at those coincidence detection events, I can be sure that on B, I'm detecting really single photons. So this is how we create these heralded single photons. So a click on A heralds. Heralds means shouts or claims or yells. So a click on A yells that a single photon has been created on A. So a measurement on B at the same time will inevitably come from one photon. So this is how we create artificially single photons in the laboratory. And then if a vertically polarized photon comes in, which is the quantum state ket V, I represent it by quantum state ket V, I can obtain two horizontally polarized photons. If a horizontal polarized photon comes in, I can create two vertically polarized photons. This is called down conversion type 1. Now, if I input a superposition of V and H, which is a diagonally polarized photon, I can create a superposition of HH and VV, which, as you all know, is a Bell state. It's an entangled quantum state. So this is how I can create entangled photon pairs. And these crystals, when you order these crystals or grow these crystals, they have to be cut in a specific orientation because you really need to know the angle at which these photons are coming out, because you can't see the photons. These are at 810 nanometers. So they do not appear on a normal camera which operates in the visible regime. So you really need to point your single photon detectors and look at electronic pulses that are received on a computer. So everything is working in the dark. So you really need to be sure what angles are you looking for. And that depends upon how the crystal is cut. So this is a subject in nonlinear optics. Or in isotropic crystals, how do you cut crystals and what is the matching angle and so on. So now when you have these down converted photons, these photons actually emerge in cones. And each point in a cone, say B1 and B2, they are correlated with one another. And this outer ring is entangled with the inner ring. And you can image these rings as well on a camera. So these are images of entangled photons that you can generate inside the laboratory. Now, first of all, you have to do alignment. Alignment is really, really crucial. So alignment is done by a back propagating laser. So you have an alignment laser that starts at the detector side and pushes light through the optical fiber into free space. And then you hit the bull's eye target, which is the center of the pair of crystals. So this is how you align each arm, A arm and B arm, before you proceed with experiments. You do some initial tests of alignment, and it all works when your counts are independent of the initial polarization. So these are technical details. I don't think they're needed at the moment. So what is quantum about this light? So how can we tell that light is quantum mechanical, and it defies classical rules? Generally, the light that we see is classical, and it could be of three kinds. The normal light that we see is called super Poissonian light, which is shown in this green curve. So this is a curve of the probability distribution of the number of photons received in a fixed interval of time. So if you look at light from, I have a light bulb in front of me, I have these fluorescent tubes, I have the sunlight. If you take a time interval and just count the number of photons impinging upon a detector in a certain amount of time and look at the variation and plot this probability distribution, I get a super Poissonian curve, which is represented in green. If I use a very fine laser, a coherent laser with a long coherence length, which does not have any intensity noise, it's pure monochromatic source of light, I get this blue curve, which is called Poissonian distribution. The property of a Poissonian distribution is that the deviation, or the standard deviation in the number of photons, is equal to the square root of the mean number of photons. This is how you kind of classify light. If this rule is followed, the light is Poissonian. So all classical sources are either Poissonian. Poissonian is the best classical light that you can get. But most of the sources are chaotic or super Poissonian. But if you can shrink this uncertainty, if you can really shrink this uncertainty to a narrower distribution, you will get sub-Poissonian light. And the sub-Poissonian light is quantum mechanical. It defies classical constructs, and there are ways to test that. So now one way of creating single photon light, you might argue, is that if I have a very small intensity, a really feeble laser. So here I'm showing a laser that has an intensity of a picowatt, a power of 1 picowatt, which is 10 to the power minus 12 of a watt. Normal pointer that you use for your presentations, they have intense powers in about 4 or 5 milliwatts or 2 or 3 milliwatts. So picowatt is a very feeble laser. So one might argue is that the intensity has been attenuated to such an extent that on the detector, 1 photon comes at a time. But if you look at the statistics of this weak intensity light, so this is my time axis, and I break up this time axis into small chunks. So weak light really means that I have a chunk with a photon, and then I have empty chunks where no photon arrives, and then another chunk with a photon, another chunk with a photon, and then 2 empty chunks, a chunk with a photon, 3 empty chunks, and so on. So even though light is sparse, the occurrence of the photons is still random. And if you plot these statistics, it will look like a Poissonian curve. So even though weak or dim or highly attenuated light might appear to be single photon or quantum mechanical light, it's still not a number state. It's still not a Fock state. The variation in the statistics of this kind of light is still Poissonian. Now, if you were to have really sub-Poissonian light, there has to be regularization of the statistics, which means 1 chunk with a photon followed by 2 empty chunks, then a photon, 2 empty chunks. So there is repetitive, periodic arrival of the photons. And this is what it really means when we say that light exhibits sub-Poissonian statistics. And such a light will be modeled by a Fock state or a number state. It will have sub-Poissonian statistics. We also call such a light anti-bunched. So here you see bunching means that photons try to coalesce, they try to come together, and then there is a large empty period. So generally classical light which exhibits Poissonian or super Poissonian statistics is bunched. Sub-Poissonian light which exhibits quantum statistics is anti-bunched. And suppose you have anti-bunched light, sub-Poissonian statistics. If you have imperfect detectors, then this regularized stream of photons will start appearing random. So you really need to have very high efficiency detectors to make everything work as well. So these are certain experimental constraints that you need to have. So this is what I've said in a tabular form: the photon statistics, the property of light, and these are certain examples. Now, the kind of metric for measurement is with what kind of light it is the second order correlation function, G2 naught. And G2 naught is a correlation function. So if light comes in and it falls on a beam splitter, then there are two output ports, a transmit port and a reflect port. If light is truly in a single photon state, then if detector B clicks, B prime will never click because the photon cannot be split. The photon cannot be detected twice. A photon can only be detected once. That's what is meant by a single photon state. If, on the contrary, B prime clicks, B will never click. But if you have super Poissonian or Poissonian light, then photons coming in here, it's possible that half of the photons go to B and half of them go to B prime. Then both of these detectors will click. So if you have perfect anti-coincidence between B and B prime, which means that they never click at the same time, then you would be sure that the light that is coming into the beam splitter is in a quantum state. It's quantum light, it's in a number state or a Fock state, and it will exhibit sub-Poissonian statistics, and the occurrence of the photons in that beam of light will be anti-bunched. And this is all kind of characterized and embodied in this mathematical relationship called the second order correlation function, which is a correlation between two intensities at the two output ports at different times, and then you normalize. And if you want to look at the same time, you just kind of put tau equals to 0 and you get a product of two intensities. And if you're talking about single particle events, the product of intensities is the probability, joint occurrence probability of detecting events on B and B prime. So this is the second order correlation function that we aim to find. It's a ratio of the coincidence and normalized with the single events. If you really want quantum mechanical light, you want this number to be 0 because there are no coincidences between B and B prime. If light is classical, then B and B prime are independent events, which means that the numerator will become equal to the denominator. It will simply become equal to the product of the two probabilities, and your correlation function will be equal to 1. So if you have a correlation function equal to 1, this is Poissonian, nice, coherent, classical light. Generally, you have super Poissonian statistics in which this number is greater than 1. But if this number is less than 1, you cannot explain this classically. It really means that you have quantum light, sub-Poissonian statistics, anti-bunched, or single photon states or number states. So this is how we actually do our experiment. So we shine light onto the pair of crystals. Two beams emerge, and then we put our beam splitter into one of the beams, and we only look at anti-coincidences between B and B prime when there is a concomitant, when there is a simultaneous detection event on A, so that we want to be truly working with single photon. So we need to herald the existence of a single photon in this branch, and that is heralded by this other beam. So we look at threefold coincidences, A, B, and B prime, and we want this number to be 0 in order to kind of verify the quantumness of light. So if we were to do this experiment by changing our coincidence window, you observe here the values of G, second order correlation function. They are very, very close to 0, but much smaller than 1, and they're smaller than 1 by 41 standard deviations. They're smaller than 1 by 22 standard deviations. This number is smaller than 1 by 343 standard deviations. This number is smaller. It deviates from the classical threshold by 310 standard deviations. Now, these are very large confidence intervals. In particle physics, you're dealing with confidence intervals that are hovering around 3 or 4 standard deviations. Here, in a tabletop, an experiment, a student experiment, you're doing a quantum mechanical experiment, and you're deviating from classicality by these huge intervals. By the way, why is this number not equal to 1? Not equal to 0? It should ideally be equal to 0, but it's non-zero, yet smaller than 1. And that non-zeroness can be defined by accidental coincidences. When the photons hit the detectors, but they're not coming from down conversion events. They are coming from two disjoint down conversion events, or there is a coincidence between a dark count and a real single photon. So all of these are accidental coincidences. And these numbers that are not equal to 0, but still much smaller than 1, they are described by the accidental coincidences. And if we do not look at the A heralding photon, and we just find out the second order correlation function on just one of the arms, we get classical light. So that's why we observe that heralding by the idler beam is extremely, extremely important. And here you can see that as the tau goes to 0, this G2, which is normally equal to 1, which represents uncorrelated photons, at tau equals 0, it jumps down to 0. This is a beautiful signature of quantum mechanical properties of light. Here is another curve. If you were to do this experiment instead of using a laser and a down conversion crystal, you would do this experiment with light coming out from a light emitting diode or sunlight. You will get second order correlation functions that are close to 1. Okay. Now, with this setup, once we have created these single photons, we can ascribe a quantum state to this photon. That quantum state is generally represented by a ket psi. Now, that psi has a certain description. These are probability amplitudes. We all know complex numbers. And then we can do measurement in different bases, and we can find out what these coefficients A, B, and phi are. So we can do complete quantum state tomography with the help of this experiment. And we're looking at the properties of a single photon. We're measuring the quantum state. So these are results from some experiments that we did. We can also do all polarimetry experiments. These are kind of more technical details. But one experiment in the last 5 minutes, or I think I have 5 minutes, or how many minutes do I have until 40?
You have all the time that you need.
Okay, so I'll just take 5 to 10 more minutes, and then we'll have question and answer. So, so one really interesting experiment is erasure and interferometry. So if I have laser that comes in and it goes through a beam splitter, and then it takes two paths, and then I recombine at the second beam splitter, I will get interference. So, but that interference really means that I'm getting fringes, but I really don't know which path the photon has taken. So there is complementarity between the path and the interference fringes. If I know the path, I will lose the fringes. So how can I know the path? I can know the path by placing polarizers in the two beams and making their polarization axes different. Say one is horizontal, the other is vertical. So if I get a horizontally polarized photon at the end, I would know that it has taken path P2. If I get vertically polarized photon at the end, I know it has taken the path P1. So if I know the path, I will erase, or I will kind of get rid of the fringes. So either I know the fringes, or I know the momentum and don't know anything about the path, or I know the path and I don't get fringes. So there is complementarity between position and momentum. Momentum, the definite momentums lead to interference fringes, because the momentum is really the wavelength. You need to have a constant wavelength difference to get interference fringes. So there is this complementarity between path and momentum. And you can also cast these problems in terms of the language of information theory. If I have which path information, I know the path, I have information about the path, I will not get fringes. So these kind of diagrams at the bottom, A and B, show the two scenarios. When I do not know the path, I get B, the condition B, which are the fringes. And if I knew the path, I get no fringes. I just get a smear, a blob of photonic intensity on the screen. Now, I can do a series of experiments in which I keep one polarizer fixed, the other rotatable. So if I rotate P2, when P1 and P2 are crossed, sorry, they are parallel. When they are parallel, I get fringes because then I don't know the path. But when they are crossed, I get the condition J, which means that the polarizers are now crossed. I know the which path, I have the which path information, and the fringes disappears. So now I can also bring in one photon of light into this interferometer. The experimental results that I show you here are from a laser light. They're not single photon, these are coherent light. But what if I pump in single photons into this interferometer? It's called a Mach-Zehnder interferometer. Now, single photons can also show interference. But what are they interfering with? If there is just one photon into the apparatus at a time, it's just interfering with itself, really. So if I were to do this experiment with photons, let me come to that in a minute, a kind of A side. So suppose I have crossed polarizers, right? P1 and P2, I get the scenario A. No information, I have complete information about the path, no interference. Now, after this photon or light has passed through the interferometer, I insert a third polarizer, P3. Now, this polarizer is coming after the interferometer. So whatever the photon wanted to do, it does it. It makes up its mind inside the interferometer, whether it would like to exhibit interference properties or not. But after the photon has emerged from the beam splitter, the interferometer, the action of another element, which is probably remote from the interferometer. This interferometer can be far away from the detection point. This kind of distant polarizer is kind of rechanging, unwinding what the photon has done in the past. And if this polarizer P3 is placed at 45 degrees, I will recover the fringes. Recovering the fringes means that I've erased which path information. That which path information was imprinted into the photon by the crossed polarizers. So the crossed polarizers obtained which path information, all right, and the photon left the interferometer, went to a far off detection point, and then just before detection, there is a polarizer that kind of unwinds what the photon has done in the past, and interference fringes are recovered by erasing the which path information. So P3 can be very far off. So if you have light coming from a galaxy and it kind of bends around a gravitational lens, an intervening star, you can change whether the photon takes either of the paths or it takes both paths by just having a detection, something under your control on planet Earth, and you're controlling how the photon has traversed its path in the past billions of years. So this is really an interesting delayed choice version of the erasure experiment. And all of this can actually be done inside a laboratory. So we build these interferometers, but instead of a Mach-Zehnder interferometer, which is slightly difficult to build, we have a kind of collinear arrangement in which we use two polar beam displacing prisms, which act like the beam splitters, and then a halfway plate in between. And then you can control which path the photon takes. So you do all kinds of things, and you can get interference fringes. And look at this polarizer P1. This polarizer P1 is kind of outside the interferometer. And by changing the orientation of the polarizer P1 to 45 degrees, I can increase the visibility. The visibility of the fringes means how big the fringes are. A visibility of 0 means no fringes. So this is a demonstration of the erasure experiment. And the nice thing is that I can keep this polarizer fixed and exploit entanglement. So now I have two beams and I change the polarizer on the first beam, HWP3. And that determines whether I see fringes of this photon on the other beam. Now, this is absolutely stunning. I'm doing a remote experiment in which I keep everything in this beam fixed. And I'm doing something remotely at a far off location, perhaps changing the polarization of a polarizer, and that determines whether I'm seeing fringes on this path or not. Now, this is an absolutely beautiful hallmark of entanglement, remote action. Einstein would have been confounded by this. He would have kind of been baffled that this is action at a distance. You're doing something far away, meters away or centimeters away, and that is controlling whether you see fringes on a different path. The two photons are actually spatially separated. So this is an example of exploiting entanglement for doing erasure experiments. And these are the results from this experiment. Still, you see interference and quantum erasure. By remote switching, you can do all kinds of nice experiments. And since now the machinery is in front of you, you have quantum states. These polarizers, rotators act like unitary operators, and then they transform, and then you get a final quantum state, and then you do a projective measurement. Everything can be done very neatly on quantum mechanics. So whenever you study a standard quantum mechanics textbook, Zetterli, Lebov, whatever is kind of you're fond of using at the University of Jordan, everything can be implemented on these tabletop experiments. You can also look at non-locality. These are kind of slightly more complicated tests. Non-locality is this idea that doing something at one location is going to affect another thing which is entangled, but at a different location. So there are tests for non-locality, and if you do different kinds of tests, we get metrics that violate locality and realism. We can do, these are called the famous Bell's tests. So we can do a CHSH test, a Hardy's test. We can also do complete quantum state tomography. We can do quantum process tomography, and so on. So this is my presentation, Dr. Hanan. I would like to end here, and I would just like to kind of invite questions and any other comments. I've been very fast here. I'm sorry about that. But the idea was just to give you an overview that simple experiments are possible with simple resources. I cannot say that all of this comes at a shoestring budget. It still costs you something, but all of these experiments are within our reach. And I think universities around the world, and especially in the developing world, really need to establish some laboratories that can show quantum mechanics. We are latecomers in the understanding of quantum mechanics.
Thank you, Dr. Sabieh.
Yes, please. Yes, please.
Okay, so we can open. Thank you, Dr. Sabieh, again for this very nice talk. I can see some hands clapping. I will unmute everybody, so everyone will be able to unmute himself. And please, if you have comments, questions, could you please raise your hand so we can offer the mic one by one? If anyone have comment, question. I think I did unmute everybody, or at least allowed everybody to unmute himself. Or you could raise your hand. Yes, I would start with Muhammad Ahmad. Yes, Muhammad, please unmute yourself.
Assalamu alaikum. I have a couple of questions about entanglement and the way that he explained that the photons, after they go through the experiment and they are used to what exactly?
Sorry, Muhammad. Can you repeat your question?
Can you carry on a little bit?
I didn't understand after we do the entanglement and the photons are being what happens to them exactly? I didn't understand the point after that.
All right, so let me share my screen again. Okay, just a minute. So let me give you the big idea again. All right, so there's a screen in front of you at the moment, Mohammed Ahmed. So what we have is, you see these red kind of beams, red colored beams. So these are entangled photons, right? And they can have a quantum state description of this kind. So first of all, you can generate these entangled photons. All right, Mohammed Ahmed? Through this down conversion process. Now you can do anything you like with these photons. Now you have a quantum state in front of you, and these are single photons, in fact, a pair of single photons. And you can do all kinds of tests for non-locality. You can test whether they are really entangled. You can do quantum computing with these photons. You can measure these photons. So now you have a resource available to us. So entanglement is a resource which is used in quantum computing, quantum information processing. So what I have shown is that, number one, you can generate these photons in the laboratory easily, very easily. Second, I've given you some examples of how interference takes place between photons, how quantum erasure takes place, how non-locality is manifest in an experiment, which means that you do something on this arm, at the top arm, and it affects, apparently there is no connection between the two photons in the classical sense of the word, but you do something, you change this element, for example, on this beam, it affects what you see on the other beam, even though there is no communication between the two photons. So this is a hallmark of entanglement. Once you have entanglement, you can do teleportation, which means you can transmit a quantum state from one point to another. You can do super dense coding, which means you can encrypt your classical message in such a manner that they are very hard to decrypt. You need another quantum computer to decrypt them. You can do completely secure quantum cryptography and communication. So entanglement is a big resource. So what I'm trying to show in this lecture today is, from an educational perspective, it's easy and straightforward to do these experiments, create the entangled resource, and then work from these photons from this point onward.
Thank you very much.
Who else? Reem, please unmute yourself.
Yes, hello. First of all, thank you so much, Doctor, for this fascinating talk. I have a question about quantum computers. Now they're being developed and they're really fast. They can solve things that normal traditional computers would take decades to solve. So my question is, are we getting closer to being able to experimentally verify the interpretation of quantum mechanics, one of the four interpretations? For example, the many worlds theory. There was a theory by Hilo Everest that we could actually experimentally verify the many worlds interpretation of quantum mechanics with quantum computers, because there's an interference between the universes, and the quantum computer, would be able to remember it. Is this a mathematical fantasy, or are we getting closer to being able to experimentally catch up to theories?
Right, so quantum computers are becoming more and more sophisticated. First of all, we're building bigger quantum computers. We have broken the ascendancy limit, which is a minimum number of qubits that are required to do something useful. We are enhancing the fault-tolerant capabilities of quantum computers. Currently, we are in what is called the NIQ regime, which is the noisy scalable quantum computing regime. So we are working with noisy data, noisy qubits. So things are improving, no doubt about it. Some applications of quantum mechanics, of quantum computers, kind of currently involve, say, finding the states of energy levels of molecules, simulating nature, looking at interactions between molecules, which is especially important for drug discovery. They're being used for cryptography. We're doing quantum communication in our real life with quantum concepts. So they are becoming more and more powerful. Still, I do not know if we will be able to kind of in the next 5 years build truly fault tolerant quantum computers. As far as your question about the many worlds interpretation is concerned, you see, when you do a computation with a quantum computer, it now is the interpretative perspective of how would you like to explain those results. So there are certain experiments such as in what is called counterfactual quantum computing, which implicate a many worlds interpretation. So, but at the moment, as far as I can answer your question, it's still interpretative. There's no undeniable verification that, all right, this experimental outcome from a quantum computer proves or validates the many worlds interpretation. So it's still at the level of interpretation.
May I ask, what do you mean by interpretation? Are the data being kind of manipulated in a way, or?
No. Interpretation really means, so once you do an experiment, the outcomes are clear. Now but physicists are not kind of satisfied and content with just looking at the outcome. They want to see if it has a bigger meaning. For example, when you do experiments which are called the verification or the violation of the Bell's inequalities, you get violation of the Bell's inequalities, which now there's an interpretation for those outcomes. The interpretation means that this nature cannot be defined as in terms of local realistic models, which means it's non-local and it's not realistic. Realistic is a special philosophical meaning. So once you get the experimental outcomes, you want to get some significant meaning out of it, how nature acts, how nature reacts, what are the culpability of nature, what is the observability of nature, can you probe deeper into the nature. For example, this question of many worlds is at the moment interpretative. So you get a measurement and you get different possibilities of outcomes. So the Everett's idea is that you get one outcome, so your wave function collapses into one state, but other universes are also created in which the other outcomes exist, but you don't live in that universe. Now, this is an interpretation as far as I can tell. Now, can an experiment be designed that can verify or falsify this interpretation? That's another thing. So interpretation is not kind of distortion of the data. The data is there. What meaning do you get from this? What is the purpose of this? What is the maqsad of this? That's what interpretation means.
Okay, thank you so much.
Thank you, Reem. Other questions? Samia? Yes, please, Samia.
Assalamu alaikum. I'm
Walaikum salam.
I was studying about SPTC setup, and I want to ask about the setup. I came across a paper in which they have placed a BBO after a laser, and then they have used another BBO. So my question is why they have used two BBO in a line.
All right, so we also use two BBOs and their optic axes are perpendicular to one another. So one BBO is such that if you input H, it creates two VV photons. The other BBO crystal is such that if you input V, it creates HH photons. So if you want entanglement, you input H plus V, you will get HH plus VV. So this is just a clever way of creating entangled states. You can also create non-entangled but correlated states, separable states, which are also single photon using a single BBO crystal. So just a clever way of creating entangled states.
Thank you. But how we will know that a BBO is placed in which manners to create HH or VV or HV photons?
All right. So let me kind of share my screen in a minute. I can show you how we know that. So
okay, thank you.
It's already shared, Dr. Sabieh.
Yeah, it's already shared. So here, just a minute. So this, if the screen is in front of you here, okay, sorry, I have to go back. So if you get an output which is independent of the orientation of the initial half-wave plate, you will know that the BBO crystals are placed in an appropriate fashion. So and when these crystals come to you, they have their optic axis marked on them. So they're cut in a special orientations, and so you know what the optic axis is. There's a marking on the optic axis because when you grow the crystal and they cut in a special direction, you know what crystallographic faces have been exposed. And you know what the optic axis. So first of all, you have a physical, by looking at the crystal, you can tell what's the optic axis. And then you kind of rotate them by 90 degrees. And then you place them inside your beam. And then you change your initial polarization through a half-wave plate. And then you look at the variation. If there is no variation, you verified that the BBO crystals are in the precise location that you desire.
Okay, sir, thank you. Now I got it. I have another question. Sir, I have tried this SPTC process on quantum fly trap because I don't have any access to the lab. So can you tell me a way in which I can perform it on my PC? Another way.
So through simulation?
Yes, sir.
So you want to do simulation? So
yes, sir.
So if you look at certain programming softwares like Qiskit is very popular these days. They start from an initial state. So you can just input whatever initial state that you want. You can input an entangled state, a separable state, a density matrix which is mixed. So you can just input any states that you desire, and then you can do your computation or quantum algorithm with it. So now these softwares exist. Q Sharp, which is produced by IBM. Rigetti has a software, and Qiskit, of course, is very popular these days. Python has inbuilt packages for quantum computing. So all of these can admit different kinds of quantum states if you want to do a simulation.
Okay, sir. Thank you very much. Thank you for the lovely talk. Thank you.
Other questions? Comments from the audience? Our students, instructors. Samia, do you still have a question? I can see that you raised your hand. Okay.
Sorry, I don't. Sorry.
Okay. Other questions, please? Comments? I would like to ask a question, Dr. Sabieh.
Yes.
First of all, you kept using the phrase that heralded photons, heralded single photon experiment. So can you explain in the easiest way you could for everybody why it's called heralded single photon or heralded single photon experiment or single photon resources? Of course, we don't see this phrase in our textbook of quantum mechanics, but I know it existed. It's not a new concept, but it doesn't exist in the textbook of teaching quantum mechanics. So can you elaborate why why heralded single photon experiment or device?
So generally when you want single photons, the most direct way of getting single photons is, say you have a quantum dot. A quantum dot is an artificial atom, and you excite that atom, and then when it de-excites, it emits a photon, a single photon. All right. So if it does that if it does that in a controllable fashion, which means you have a switch, some kind of switch that can control when it emits a single photon. So you shine a laser light, the laser light excites that atom, and then it fluoresces through a single photon emission. So this is a true single photon source. Whenever you input your laser pulse, say after a few nanoseconds, which is the lifetime of the excited state, a single photon is emitted. So this is a true single photon, and you can work, these are quantum states, they will be sub-Poissonian, they will be anti-bunched, they will have a second order correlation function which is close to 0, less than 1. So these are true single photon sources. But they are very hard to build. Generally they require low temperatures. They are built in magneto-optical traps. You need to have an elaborate setup. Everything has to be cooled down. You need some kind of laser cooling, Doppler cooling to kind of cool a cold molasses of cold atoms down to very low temperatures to the millikelvins regime. And then you shine a laser pulse and then you get these single photons. Now these experiments are hard to build. And they're, of course, kind of really, really expensive. So how in the laboratory with our students, how can they see single photons? So how they see single photons is that a beam of light from a laser is falling onto two BBO crystals. And those BBO crystals have a very small efficiency of creating photon pairs. That efficiency is 10⁻⁻12, say. So if you have 1 watt of laser power coming in, 1 picowatt laser power will go into the down converted photons. Now those down converted photons are kind of produced in those two beams. Now heralding in English language means shouting. So if you have a classroom,
yes,
immediately a student comes in and the student wants to identify himself or herself, he heralds to the teacher, I'm here, I'm here. So this is heralding. So what happens is that you have 2 photons coming in and you use one of your photons as a heralder, as a shouter that announces that I have come, I'm here.
As a celebration.
As a celebration. So I'm here. So if a twin photon exists on the other beam, then that photon, you know that both of those photons have come from that down conversion process. They are produced in an entangled pair. And you can do experiments on that one photon, which is conditioned upon the presence of a heralding photon, and you would know that these are truly single photons. So this is the concept of heralding. So this is a kind of cheap.
In Arabic, can you find the word for heralding or heralded? I think it's like bushra.
Yeah, it's like bushra. It's not necessarily excitement. It's not necessarily happy news.
Not necessarily excitement, but it's an announcement of something that just happened.
Exactly.
It's kind of announcement.
It's call for attention. It's call for attention. It's a nida.
Call for attention. Call for attention. Yes. Okay, thank you. And from the title, we said that quantumness of light is explored in the physics curriculum through experiments. What are the name or the names of courses that you expose the student to this single photon quantum laboratory in LUMS?
So in LUMS, we have 2 main courses for physics experiments. One is a course on the freshman course, which is the first year course, which every student takes: chemistry, biology, mathematics, physics, computer science. But then in the 3rd year, there is an advanced lab course. So this sequence of experiments, we have 8 experiments. And the 2nd edition of our book has also been published, which is an updated version of the 1st edition. Those 8 experiments are followed to a group of students in the advanced physics laboratory, which is in the 3rd year of their undergraduate studies. MS students also take this laboratory. So currently it's a part of an experimental physics course, lab course, a hands-on course. But it can also be made a course on its own. So if you have a quantum mechanics course, 3 credit hour quantum mechanics course, and 2 quantum mechanics courses, 3 + 3, you can have a 2 credit hour laboratory course as well. kind of associated with it.
Thank you. Any
But
other comments?
I'm noticing one thing, that
yes,
quantum mechanics and quantum physics is not just the purview of physics majors, and it's not just the purview of university students. I've become more and more aware of pre-university students learning quantum mechanics, learning about quantum computing. So gone are the days then this is a specialized area. And I think there's a new movement in the physics community which is called pictorial quantum mechanics. And in quantum pictorialism, they use cartoons and diagrams in a sophisticated and methodical fashion, just like Feynman diagrams, to teach quantum mechanics. So every school student, even though he or she knows nothing about quantum mechanics, just a little bit of linear algebra and matrix manipulation, with the help of those pictures and diagrams, can easily understand quantum mechanics. In fact, there was a study which was done in England, which was also published in the newspapers, that they exposed Oxford University students and pre-university students from high school to the same curriculum based upon pictures. And the high school students did actually better than university students. So university students should not really feel really elitist and proud that they are the only ones who know quantum mechanics.
Unfortunately, university students, when they finish the school, they feel relaxed. So they let's say, lower their efforts, their potential, because they feel relaxed. They got the achievement. They got enrolled in the university. The dream came true. So that's why maybe the school students excelled over them.
Yes.
But still, the main challenge of teaching quantum mechanics, that it's like stereotyped as an abstract subject in physics, which is not true. I do believe that quantum mechanics is applied physics, is experimental field of physics. But unfortunately, how it's it's pictured in the curriculum, and also through physicists themselves, it's reduced to students as abstract subject.
Yes. So traditionally, the textbooks on quantum mechanics are written in a very old-fashioned manner. They work on the historical progression and so on. But there are new textbooks that are coming up, which kind of start off with either the quantum information perspective or the experimental perspective. Nanotechnology, which is considered to be a realm of material science, can also be taught in a very quantum mechanical way. So quantum mechanics is everywhere. Optics can be taught. Optics can be a good introduction to quantum mechanics.
Yes,
I would also
optics.
say.
Yeah. But don't you face that challenge even when you try to transform? I know that you were one of the those who established the physics department in LUMS University. But even if you try to initiate a transformative change in the curriculum, or you get let's say, you get challenge from those who don't like to change. So, for example, if you introduce a new textbook rather than the textbook that all previous professors were teaching, you will get criticized from your colleagues and your students also. They don't want to change.
See, Dr.
I always
Hannan,
tell them our role in teaching modern physics and quantum physics. Now I'm teaching a course on modern physics. I keep saying to my students, maybe some of them now hear me, that my role is to show you the surprises of modern physics. But you can read it. I just guide you to show the surprises of modern physics that also astonish me up to date. But when I try to change something, you get this, let's say, this conflict with the atmosphere that you are working on. Nobody wanted to change.
You see, Dr. Hannan, you are in.
So how you overcome this?
Yeah, so you are in a big university. You're in a public sector, big university, maybe
relatively
thousands of students at the University of Jordan.
About 50,000.
About 50,000, right? So it's a big number. And you have a big physics department.
More than 1,000, maybe 1,500, something like that.
How many in physics?
Physics, around 30. We are a bit less than 30 nowadays.
Right. So we are a small school and a small university, as you know. We are a small department, 7 or 8 people. And all of them are of the same ideas. They share the same philosophy. So we do not have a problem. Actually, we are in a kind of paradise.
Mashallah.
in our university. So we
Mashallah.
are in a paradise. But I can understand what you are saying. In Pakistan, I mean, the physics is kind of, the problems that you mentioned, they are there, but they are slightly being changed. The problems are slowly being overcome, because when you get a large number of teachers who are trained from the best places in the world in one department, the majority define what needs to be taught. And when youngsters come into a department, they kind of shape the direction of that department. So things will change inevitably. It's a cycle, but things will really change. You see, 30, 40 years ago, in our, say 40 years ago, there were many universities in Pakistan where there was not a single teacher who could teach quantum mechanics. See, so things change, but now the situation is slightly different. And this also holds true, by the way, for other sub branches of physics: statistical mechanics, electromagnetism, electrodynamics, mechanics itself. So all of these realms face similar problems, I think. So you need more youngsters, because without youngsters, without kind of new blood coming into the departments, things will become ossified. Things will be hard to change. And you need youngsters who become the heads of departments. So this is the one thing that is needed. You need people with a fresh outlook to become heads of departments, not seniority. Seniority does not qualify you to become a leader. So when we change this mentality, things will change. And this is very hard to say sometimes.
It's hard to say, it's hard to do, at least in my region, I would say. I wish that one of our students, I can see some names, who would ask you a typical question that connecting this field to modern physics and quantum mechanics. There is a common quote of Niels Bohr that he said, if you have not been shocked with quantum mechanics, probably you have not understood it. So people took this from a positive point of view or from a negative point of view. So even some teachers, when they start with this quote, they would like to reflect that this means you will never understand this course. This is for genius only. But also on the other positive sides, which is, I mean, what I believe in, that it's also reflects that it's full modern physics or quantum mechanics. It's full of astonishing results. But this doesn't mean it's not real. It doesn't mean that it's not touchable. It doesn't mean that it's not understandable. So what do you comment about that?
I think it all depends upon the teacher, how he or she presents the surprise. So if the teacher is surprise really here means fascination and excitement. So you can be surprised by a negative thing as well. A shock is also a surprise.
Right.
God forbid you hear a shocking news, it's surprising for you, but it's also shocking and demoralizing. So surprising here really means fascinating. So the teacher has to be fascinated about it. And I think the best teachers who are motivated, they should do the first course, the modern physics course. When we teach modern physics, we start with interferometers. We don't start with the Thomson model or the Rutherford model or the atomic spectra or the Compton effect. We don't do that any longer. We just start with interferometers and we take a very information perspective view. So, everyone wants to do computer science these days. So it really helps to take an information theoretic perspective talk about Nobel Prize winning work, talk about interferometers. Photons are a good mechanism of introducing quantum mechanics, and they don't need a lot of background as well. So it all depends. Get your best teachers to do your basic courses in the first year.
Thank you, Dr. Sabieh. I don't know if the audience could raise other questions or comments. I can see there are still more than 50 people with us.
So if anyone wants to come and work in our laboratory for 2-3 weeks, some committed student who wants to learn about this, just let me know. Let Dr. Hanan know, and we can arrange something. Inshallah, I'm very hopeful that we can arrange some funds for a visitor for 2-3 weeks. If someone is really interested in knowing about this and learning about this hands-on, summers is a good time when people can come. This is an open offer to the LAMBDA physics community.
Thank you very much, Dr. Sabieh. By the way, in the introductory speech, Jude mentioned that next year, 2025, the world will be celebrating the International Year of Quantum Science and Technology. And here in the University of Jordan, we will be celebrating the first decade of LAMBDA. So for us as LAMBDA, you contributed to our engagement and outreach activities. And we hope next year we will, I hope in person, but at least if not in person, we could meet in some of LAMBDA events celebrating 1 decade of LAMBDA. So before we close, I would like to thank Dr. Sabieh again for the time and the effort and for being always generous with the LAMBDA. You always sent me. I cannot say no for you and your students. I'm very grateful for that. And I hope we welcome you again in Jordan or we visit you again in Lahore. It will be a pleasure. And I would like to thank also all the participants who joined us from the University of Jordan, from Pakistan, and also from the region. And we hope that you also join other LAMBDA events in the upcoming year, in person, on campus, or online. So if you see on the invitation letter sent to you, you can find the LinkedIn webpage of LAMBDA, the website of LAMBDA, and the YouTube channel of LAMBDA Physics Group. Inshallah, if this recording went successful, the full lecture will be also shared on LAMBDA YouTube channel. Reem, would you like to say something on behalf of LAMBDA before we close?
Yes, thank you so much, Professor, for your generosity and your amazing talk. We learned so much. It's very fascinating, and it would definitely drive curiosity and for us to research more and learn more. It was very motivating. Thank you.
Thank you, everyone. Thank you, Dr. Hanan. Thank you, Jude. Thank you, Reem, and all the participants.
Thank you very much, Dr. Sabieh.